Hello, my dear students. Today I am going to discuss about the residue of f of z at a pole. Residue of f of z at a pole. So, the definition of residue of f of z at a pole A is we shortly written residue means res of f of z at z equal to a is equal to 1 by 2 pi I integral over c f of z dz, where c is a simple closed curve containing the only singularity z equal to a, that is isolated singular point z equal to a in the given simple closed curve c, and c being taken anti-clockwise direction. So this is the classical definition of the residue of the given analytic function f of z at the pole z is equal to a. Okay, now how to find this residue values, how to get those residue values? Yeah, let us see evaluation of residues. There are three types of formula. The first one is about simple pole. Suppose the pole is of order 1, then the residue of f of z at z equal to a is equal to limit z tends to a z minus a into f of z. This is nothing but the definition of order of the pole. Remember, limit z tends to a z minus a into f of z. That limit value is nothing but the residual value of f of z at the simple pole. Suppose when we have the order of the pole is 2 or 3 or 4 or generally n, then the residue of f of z at z equal to a with the order n, see the third formula, is equal to limit z tends to a, limit z tends to a, what is order n? N means 1 by n minus 1 factorial, 1 by n minus 1 factorial. Differentiate n minus 1 time. You see the order is n means differentiate n minus 1 times the value z minus a full power n into f of z. So differentiate this with respect to z n minus 1 times. After that, applying the limit value as z tends to a. So this is the general formula. Now the beauty is, when I substitute n equal to 1, which gives the first formula, you see, when I substitute n equal to 1, what we hear, n equal to 1, 1 minus 1, 0, 0 factorial is 1. Here also 1 minus 1 is 0, so no derivative is required. Z minus a full power n into, it is 1 into f of z. So that is the first formula. Got it? So this is the general formula of order n. We put n equal to 1, we get the first formula. N equal to 2, 3, 4, yeah, you can use it for any order value. The another one is the second formula is the special type. Suppose the given function f of z is not looks like a polynomial types, looks like something like a trigonometric, then or even exponential, even logarithmic functions, then the second formula is really used when we have such functions. What is f of z? Some g of z by some h of z, right? where g of a is not equal to 0, because when you substitute z equal to a, so denominator equal to 0, that is the pole, but denominator is not equal to 0. Now what is the residue of this f of z at the pole z equal to a is equal to limit z tends to a g of z, so there is no changes in the numerator, but the denominator we differentiate one time with respect to z, so h dash of z. Okay, this is the special case. Let us see some problems so that you can easily understand how to find or how to get or how to compute the residual value of f of z at their poles. So this is the some questions. Determine the residue for the following at each of its poles. Correct? So already we have seen some examples. This is the example for the pole z equal to 2 of order 1 and minus 1 of order 2. So apply the formula, we will get the answers 4 by 9 and minus 4 by 9. So these are some problems for your practice. Z squared by z minus 1 whole squared into z plus 2. So what are the poles? 1 of order 2 minus 2 of order 1. Got it? So let us see the answers. So there are many problems are listed here. Clear? Find the ratio or find the residue at z equal to 0 of the following functions. So it is clearly given that z equal to 0. Z is equal to 0. So when you substitute z equal to 0, we get 1 by 0 is infinity. So e power infinity is infinity. Got it? So let us see the first problem. Yeah. E power 1 by z. So expand this with the help of the exponential function. It has 1 plus 1 by 1 factorial, 1 by z. So there are how many number of terms are there? There are many number of terms are there, isn't it? Now when I apply limit z tends to 0, everything becomes infinity. So this is the way to find out the residue of f of z at z equal to a. Generally here there is no denominator, so we can't apply the formula like limit z tends to a z minus a into f of z. But at that time we can express the given f of z as a Lorentz series expansion, and the residue is nothing but the coefficient of 1 by z in the Lorentz series expansion. So here the answer is 1. Got it? When you directly apply z tends to 0, what happened? 1 by 0 becomes infinity. Infinity. Got it? So coefficient of 1 by z in the Lorentz series expansion is nothing but the residue of f of z. This is the another technique. See this is a second example. Sin z by z. Use the sin z expansion, multiply 1 by z power 4. Already we know that z equal to 0 is the pole of order 4. I don't want to use the formula. If it is possible to expand, this looks like a Lorentz series expansion and collect the coefficient of 1 by z. So after this we found that the coefficient of 1 by z is 1 by 3 factorial, that is 1 by 6, that is minus 1 by 6. So this is the easiest one, but this cannot be possible in most of the cases, right? Third one, z into cos of 1 by z. Use the cos z expansion, multiply z into the term, we get this one. It has an infinite number of negative powers of ez, and what is the residue of f of z at the point z equal to 0? When you put z equal to 0, it's not possible. So limiting case fails completely, isn't it? So that's why this technique is used when the limiting cases fails. So what's the coefficient of 1 by z? 1 by 2 factorial. That is minus 1 by 2 factorial. The answer is 1 minus 1 by 2. So continue like that. You may find out the residue of f of z for the functions at the pole z equal to 0. So this is the some problems. I think so we have discussed first 3 problems, 1, 2, 3. The remaining 3 looks like the same way. You can use the exponential function. Here use a sign. Here we use 1 by sine. I think cosecant square is 1 by sine square. So use that idea. Don't apply the limiting idea. Okay, because when you apply the limiting cases, it fails completely here. It doesn't works. Some more interesting problems with the help of the residue of f of z, and with the help of the residue of f of z at their poles, we have one important theorem is named as Cauchy's residue theorem. Already we have seen that Cauchy's fundamental theorem, Cauchy's fundamental formula, that is integral formula, and this is the second technique. With the help of residue, we are going to establish a theorem, Cauchy's residue theorem. Let us see in the separate video lecture of Cauchy's residue theorem and its applications. I hope everyone understood this topic. Thank you. Thank you for listening patiently. Thank you so much. This is your A.D. Chandrasekharan signing off. Take care. Bye.